So, here we are at Professor and Associate Chair of the undergrad program, Pierre Mertiny's office. He's going to show us around a couple of the buildings and let us know about some of the cool stuff going on in mechanical engineering.
Oh, hi Luca. I'm gonna see where I can take you. I mean, I don't have access to everything, right? So, but let's see if you can look into the wind tunnel, maybe my own lab to see like what we do there in composite materials. Maybe you can take a peek in the engine lab because there's a lot of interesting stuff in there. And let's see if the test field is still open where some of the experiments are for like the different engineering labs.
Right. Man, you are good at this.
This is probably one of the best of all times Mickey 260 project. This is just pure genius the way this is put together with these plastic blocks and making the gearboxes. This was a project where they had like a GoPro camera up here and they had to drive around a maze and scan targets in the maze, and they got points for, you know, if those targets actually showed up on the GoPro footage. What we see here is our energy storage flywheel test bed. So we're testing like flywheels for the storage of electrical energy, like say that comes from renewable energy sources. And we want to find out like how these flywheels behave. You know, you can see inside the rotor, which is made from a fiber reinforced polymer material. I can turn this on using the electrical machine here on the top. If to slow it down, you need to put the electricity somewhere, right? So we have a bank of lights here we can use, but that's more like for show. The real way to get rid of the electricity is this big resistor, which just heats up when we slow this down. You actually don't use mechanical brakes to slow down the train, like with brake pads and friction discs and so on, but you're actually using the electrical motors on the train. Every train does this anyway because it's a much smoother way and much more long-lasting way of using the train. You don't have to change brake pads and so on. So using the motors to slow down the train is a great way. But if you use the motors to slow down the train, you generate electricity in the process, and you can store this electricity and then use it again to accelerate the train later on. So it saves a lot of energy in the operation of a train system. To turn it on, I have to put it into the concrete pit. For safety reasons, because if something goes wrong, if this has a massive like bearing failure or so, you know, we can calculate how fast the housing would spin on the conservation of angular momentum, so it would be pretty fast, and then all the cables would be flying off and so on. So it's better if this sits in a safe environment so nothing can go wrong. So this is one of our workhorses here. This is actually a materials testing machine that applies actual load or compression load on whatever sample you want to have. There's also a lot of student projects going on here, like graduate student research work. So this machine is like used all the time. It's again our real workhorse. This is one of our oldest machines, the Tinnis Olsen testing machine, where this plate is being tensioned. And you can see it's like instrumented with a gazillion strain gauges. So you will learn the theory and, you know, how the load that's being applied around a plate with a hole, what stresses and strains you will see at the point. I mean, this is an overkill machine. I think it's somewhere like 250,000 pounds of tensile force it can apply. So yeah, the sheer size of it's pretty cool. When groups tour the machine shop, they get to see this machine in action, where we pull these steel rods apart. So it's always beautiful to see that people like watch this and you see slowly, you know, the necking in the middle where the diameter gets slowly smaller, but then ultimately this thing will pull apart, and it's incredibly loud. So you see, you can't even see that, like, oh, the video doesn't do it. Like, you have to stand here and watch it in anticipation, and suddenly when this thing goes off, people jump like foot high in the air just because they're so shocked by the loud bang that this thing creates. So yeah, open house, crowd pleaser.
This doesn't have to be like confidential or anything like that.
Not yet, no. So what's going on here? I'm doing drag reduction on that, which is a simplified automotive body. It looks like a giant brick, but it's supposed to simulate a like really square-backed transportation vehicle, essentially. the wind comes, there's a gigantic turbine fan upstairs. And then,
So it goes around, right?
yeah, it comes down on that side. Or no, it goes around, comes down on that side and goes back up on this side.
So you can't. It's 2 stories high. This whole thing, right?
Yeah.
So
Yeah, there's a lot of fun stuff that happens in here.
I always wanted to do like get in there on my bicycle and fine tune my aerodynamic outfit.
You can do it upstairs, so it would fit. It's not conditioned up there, but we had a helicopter in there, so I'm like, yeah. So there's a bunch of different methods to get actual physical streamlines. You have to measure data and then put it in our fancy software. But we do have a smoke machine. Right now it's on a load cell, so that gives us all our force measurements and moments on that body. That's what I'm doing, but there's a big laser back there and it's very expensive. Class 4 laser on the other side of the wind tunnel, and got a whole bunch of high-speed cameras that we use, so we do a lot of imaging.
Favorite thing about fluid dynamics?
Favorite thing? Ooh, putting me on the spot. I'm terrible at abstracts, so that's what I like about fluid dynamics. Just don't get my socks in the video.
Alright, sounds good.
We got no shoe policy in the wind tunnel, so.
it's just an engine test stand with a dynamometer in the middle. They're looking at different fuels, injection methods. I don't know, you name it. Like if you look at the wiring of this, if you take one and change one of those wires, it's probably wreck their day before they find what's wrong, and it's gonna be it's a highly complicated system. You might have heard this story. I was invited by a friend to the University of Hokkaido, and that's one of the imperial universities, so like top tier Japanese university. So he gave me a tour, and it was like crazy crowded at all their labs and everything. And they actually built in some areas even platforms over 2x4s where like the experiments were underneath and the students were sitting on top. And he's like, so what do you think? I says, it's actually kind of messy, right? And he says, yeah, but all of this equipment that was given to us by the emperor, we can't throw it away.
Oh.
Let's go in my lab, they're pretty finished up. So another lab that we work in here is like it's a composites manufacturing lab. In this particular case, it's a pipe that we worked on a couple of years ago that is made from like a thermoplastic material. So we actually can melt the plastic with the fibers inside and then conform it to create these pipes. And so the question is like, how do you most effectively manufacture this? So we have all the industrial scale equipment in here to actually answer these questions that people have. This is carbon fiber here. So we have been working with that. Actually, the flywheel that you just saw downstairs was also manufactured here in this lab. So we use the machinery here to produce this. Fibers are so strong, and they're going in a circumferential direction, like round this way and then bonded together with the plastic. It will typically never fail by a crack that goes through the thickness. What happens is it will ultimately, a crack will develop that goes circumferentially. So that's how a flywheel typically fails. Lots of these plastics, they need to be heat cured. And to actually do this, we have this oven. And, as you saw, some of the parts are really big. And that's what the oven looks like. It's monocoque chassis from the Formula SAE team in here. And it was cured in this oven. So it's one of the bigger ovens. It's, I think, probably the largest oven on campus. This is a flywheel. The size of a flywheel you need to be autonomous with your house. So there was a project where we looked into the design of if you want to have if you have solar cells on the roof of your house and you want to be completely off the grid, you need to store electricity enough to get at least through one day, right? If there's not enough sunshine in the night, obviously, right? So how do you do this flywheel? Let's say a flywheel would be efficient enough. It's currently not. It makes more sense to use batteries for this. But if you would use a flywheel, this is the size of the flywheel.